Hello, this is section 3.3, optimization with linear programming. So in this section, we're going to find maximum and minimum values of a function over a region, and we're going to solve some real-world optimization problems using linear programming. So let's just go through the vocabulary really quickly. Basically, this is what we did in 3.2, but now we're applying it to real-world situations. So our first vocabulary is linear programming. What is linear programming? It's just a method for finding maximum and minimum values of a function over a given system of inequalities, which we call our constraints. So our constraints are what is, for instance, you might have a factory and it can only be open for 10 hours out of a day. So that's going to be one of your constraints. Then we have what's called a feasible region. We've already learned how to solve systems of inequalities, and we did it in 3.2. And when we got one that was completely closed, we said this area right here in between is called the feasible region. So it's just an enclosed region formed after our constraints are graphed and the vertices are formed. Now you have two types of feasible regions. You have a bounded and an unbounded. This first one shows you it completely closes and makes a polygon. So you got to know the definition of a polygon going back to geometry. When it's completely closed, flat shape. So this particular polygon is a triangle, so this whole area is bounded. Unbounded is feasible region that's not a polygon with a region that is open. So look at this one. We've got 1, 2, 3 inequalities. However, this side, because it goes on forever, is open forever and ever. So that's simply unbounded. And then our last vocabulary is optimize. Optimize means just to seek the best price of amount to minimize our costs or maximum our profits. So here are the steps. So let's just go through them, what you're going to do. So the first thing you're going to do, because most of these are going to be word problems, all right? So we will define a variable. We will write a system of inequalities, which are our constraints, and then we're going to graph the systems of inequalities. We're going to find all the coordinates of the vertices of the feasible region, so it's all the points that are in the bounded area, or surround the bounded area, and then we're going to write a linear function to be maximized or minimized. Okay, and we're going to learn how to write those. They're pretty simple. It's called your objective function. Doesn't tell you in the book, so write this down so I can check your notes. Substitute the coordinates of the vertices into the function. So we take all those vertices and we put them back into the objective function, and then we're going to select what we're looking for. If we're looking for a maximum, we find the largest number. If we want the minimum, we find the smallest number. And there's your answer to your problem. So let's look at example 1. So first they just give us these equations. They don't give us a word problem. They give us all the constraints, and they want us to find the maximum and the minimum values, and they give us the objective function. So notice that the objective function is f of x comma y equals 4x minus 2y. Your objective function is always going to look like that. And we actually have, it looks like we only have 3 equations, but we actually have 4 equations. So look at this first one is actually going to be broken down because it's a compound inequality. So what are our equations? Let me just go to video layer 2. So we're going to have y greater than or equal to 3 and y less than or equal to 6. So I just broke that first one that said 3 is less than or equal to y less than or equal to 6. I just broke it down to the 2 because it's technically 2. Then we have y less than or equal to 3x plus 12. And then the other one, the y less than, then we have y less than or equal to negative 2x plus 6. So we should go, remember I said name them so you know what they are. So I'm going to name this A, B, and when I previously did this, I named this C, so I apologize for them being backwards. So that's the first thing we're going to do. The second thing we're going to do is we're going to graph these. So we're going to go to our graph, and you should use graphing paper at this point because it just makes it a little bit easier sometimes to see. Still not always pretty numbers. Oops, what am I doing? Sorry. So y equals 3 is going to go through here. All right? And y, and I didn't make this graph long enough, so I'm just going to make them really small. So y equals 6. So remember, I can rewrite these, that it will help you graph them. I can rewrite these to say y equals 3, y equals 6, y equals 3x plus 12, and y equals negative 2x plus 6. Now, why inequality scare us? I don't know. But basically, I can rewrite this to graph the equations because I know they're all going to be solid lines, and then I can worry about the shading later. This one is going to come, let's see. So this is going to go through this point here and somewhere over here. So I'm just going to go ahead and do this. And then I know it's going to do something like this. So if I look at this carefully, my vertices are here. I have 4 vertices formed. And what is my feasible region? And sometimes it helps to use different colors because it can get quite nasty. So this is my feasible region. It's bounded. It's made a quadrilateral because it's a complete closed polygon. So what I need to do is I need to find these points here. So like I said, you should label what your graphs are. So this is A, this is B, according to mine, this is C, and this is D. So here, I need the intersection of A and D. We simply just use a system, and these are real easy because you just have, so this is A, B, D, and C. Because you have a horizontal line, you just put this in for Y and solve for X. So we're not going to spend time in this video doing systems of equations. This is something that you should know by now. If not, we can go over it in class. The next coordinate we want to get is the system of B and D. So the intersection of B and D is going to equal negative 2, 6. Then I want this point here, which is the intersection of lines C and B. So you would take these two and find your inequality, and you're going to get, so B and C, you're going to get 0, 6. And then the last one is A and C, and you're going to get negative 1.5, 3. So the next thing you want to do is you want to make a table. So you're going to do x, y, and then you're going to do f of x, y, which is your objective function, and then you're going to get some value over here in the table. So you put these here, 3, 3, negative 2, 6, 0, 6, negative 1.5, 3. So if we put them in our equation, I'll write the first one. So what is our objective function? Our objective function is f of x, y equal 4x minus 2y. So this is our objective. These are called our constraints. This is what limits us. This is what restricts us. That's what a constraint is. So I'm going to put 4 times negative 3 minus 2 times 3. So you're putting in this xy into this objective function. When we do that, we're going to get negative 18. When you put in negative 2, 6, we're going to get negative 20. When we put 0, 6 in, we get negative 12. And then when we put the last one in, we're going to get 0. So what is my largest number? If you look at these numbers, you got to know how to read a number line. So this is going to be our maximum, and this is our smallest number, so this is going to be our minimum. So that's simply what we do with linear programming. But we're going to have a real-world example. They're going to ask us to find something, and that's how we build our objective function. Then they're going to give us constraints or any restrictions on the x and the y, the domain or the range, and that's what these inequalities are. Then we're going to graph them, find the vertices, the coordinates of each vertice, list them, put them into the objective function and get a value. Once we do this, then we're going to be able to identify, are they asking us for the largest? Are we trying to maximize something? Are we trying to minimize something? And that's how you get these values. Okay, so pause this and do guided practice 1A and 1B. So now let's look at example 2 in the book. Okay, so it tells us, so example 2 tells us, graph the system of inequalities, name the coordinates of the vertices of the feasible region, and find the maximum and minimum values. Okay, so the first one was bounded. It was completely bounded. Now we've only got 3 constraints here, and I didn't write the objective function, but there is an objective function. So let's graph these. So our inequalities are, so the first one is 2y plus 3x greater than or equal to negative 12. We have to solve for y. Remember, it has to be in slope-intercept form. So I'm not doing the algebra here, but you get y equals negative 3/2 x minus 6. And then the other two are simply y less than or equal to 3x plus 12 and y greater than or equal to 3x minus 6. Again, I'm going to just give them names because it helps to identify them when you're graphing them. So the first one is going to go through 1, 2, 3, 4. 1, 2, 3, 4 here. And it's going to go way up here somewhere. So we're just going to go ahead and draw this line through this point. Okay, I didn't draw it very good, but it's going to go really high. So this is going to be equation B. That's this one that I just graphed here. The next one, A, is going to go through this point, but it's going to go this way. So this is equation A. And then equation C is going to go through these 2 points. And it's going to do something like this. Okay, now you'll notice I have a vertice here and here, but nowhere else. And then this is my feasible region. This is what's bounded if you graph the inequality correctly. And you notice that this is open here. So this is an unbounded region. All right, so we still are going to make our table. We're going to use our optimization equation. Our objective equation is called 9x minus 6y. So we're going to put the 2 coordinates. So these were easy. See, we don't have to do a system. So this is negative 4, 0, and 0, negative 6. When we put these into this function, so we put negative 4 in for x and 0 for y. So 9 times negative 4 is negative 36. Put 0 in for x, we get negative 6 times negative 6, which is positive 36. So this is our maximum, and this is our, it looks like our minimum, but we only have 2 values, so how can we really say? When you have an unbounded region, you can either have a maximum or a minimum, but not both. This is really important. This is unbounded. So how do we know what we have? So 0, negative 6 is right here. So this is going to be 36. This is going to be negative 36. Let's pick another point in this region, okay? So we'll pick another point, let's just say 0, 8. Let's put it into our objective function, and we get negative 48. So this right here is negative 48. And you see as we go up through the region, and you can pick another point way out here, you're going to notice that the numbers are going to continue to get smaller. Remember, negative 30 is larger than negative 48. So because they're getting smaller, that means to get bigger, they go this way. And because this is the top end, this is a maximum. So you can't just look at the graph and go, oh, I have a minimum. You have to put values in. If you only have 2, you have to find another value that goes, so your region can be open down here, then you would find one down at the bottom. And look to see what the pattern is. It's getting smaller, so it's getting bigger here, and it's going to stop right here. It's going to top out right here. Even though it's upside down, it is a maximum. So these can be a little tricky, but you just think of it that way. Look at a number line, understand numbers. Pause this and do problems 2A and 2B. The last problem we're going to look at is a real-world problem. And here, we're going to use the beginning of the book. If you look at the top here, we're going to use this based on this information. So it says, a sign on the company bulletin board is shown. If at least 2,000 items must be produced per shift, how many of each type should be made to minimize costs? So the question is going to give you the information you need to make your objective function. The company is experiencing limitations or constraints or restrictions, same difference, on the production caused by customer demand, shipping, and the productivity of their factory. So a system of inequalities can be used to represent these restraints. So here's what they got. So they're making 2 products, audio and a phone. So first thing we need to do is we need to identify what our variables are. So we have A for audio and P for phone. Okay, so these are the items we're going to make. You could use X and Y. It doesn't really matter, but when you're doing linear programming, it kind of makes sense to use the variables of the initials of the items you're doing. And they tell us our goal production per shift. So we want to make a minimum of 600 audios and a maximum of 1,500, a minimum of 800 phones and a maximum of 1,700 phones. And this is what they cost each to make. So let's first start with, and they tell us we can, if at least 2,000 items, that can be A or B, we need to produce at least 2,000 per shift, okay? How many of each type should be made to minimize the cost? So let's start with writing our equations. So we know A is audio, P is the number of phones. So we said for audio, we have to be greater than or equal to 600, but less than or equal to 1,500. For phones, we want to make at least 800, but less than or equal to 1,700. And we know we need to make a total of at least 2,000 phones and or audios. And we want to minimize costs, so our objective function is going to be f of x comma y. So our cost is going to be, okay, what do these cost? These cost $55 each to make, and these cost $95 to make. So the cost is going to be $55 times the number of audios plus $95 times the number of phones. This is going to give us our cost. There's our objective function. These are our constraints. But you notice, don't I have 2 constraints here and 2 here? So I have a total of 5 constraints. All right? So what you're going to do is you're going to graph these. And here's where we probably want to use our calculator or make sure that our graphs show some pretty large numbers. So let's go look at what that graph looks like. So we're going to let them graph it. So remember, this is A greater than or equal to 600. So the first thing we want to do, let's rewrite these. A is greater than or equal to 600. A is less than or equal to 1,500. P is greater than or equal to 800. P is less than or equal to 1,700. And then we have A plus P equals 200. So we have to first determine which is our A, which is our B. It really doesn't matter because you should get the same answers. It's just going to look a little different. So they made this audio, number of audio players, and this is the number of phones. So A is our X value and P is our Y value. So this says A equals 600, correct? Like I said, rewrite them with equalities so you're not struggling on graphing these inequalities. So A plus P equals 200. So if we go, P equals is Y equals. That's going to be some sort of horizontal line. So we say this is 1700 and this is 1500, right? Again, label them. We can call them, since we have an A in here and a P, we can call them equations 1, 2, 3, 4, and 5. You can use Roman numerals, you can use symbols, you can use whatever you want. So this one here at P equals 1700 is going to be 4, and at, oops, I did this wrong, P at 800, so this is 800. It's going to be number 5. And then these are your X coordinates, so this says X equals 600. Those are going to be vertical lines. So this is 600, and this is 800. This is going to be equation 1, equation 2. Apologize if my graph is overlapping. And then we're going to do this one at A plus P equal 200, and it's going to go through somewhere like this. Okay, so here I've got 1, 2, 3, 4, 5 vertices formed. Okay, and then my feasible region is going to be right here. So I've got to find these coordinates. Again, label them and say, okay, I need 1, 2. So let's see, does 1 cross 2? No, it doesn't. 1 crosses 4 right here. And 1, so 1, and then this one is going to be 5, so 1 and 5 cross. And then here, this is going to be 3 and 5, so 3 and 5. This one's going to be 3 and 2. And then this one's going to be 2 and 4. Now we can go, if I was neat, I would take this equation, this is 1 and 4, and I would find the so this one's going to be 600, because they're just, these are easy because it's a vertical and a horizontal, so it's just each one of those numbers. Okay, and then so on and so on. So what we get here, and I don't know if these are in the right order, so, but these are your equations that you're finding the intersection, which you're using a system of equations. So we get a total of, these are all our numbers, okay? So then we're going to put them, these are our x comma y's, we're going to put them in our objective function here. When we do that, we're going to get 1, 9, 4, we're going to get some big numbers, and again, these are real world problems. So they're talking about costs and profits, so you're going to talk sometimes millions and billions of dollars. So you have to know your numbers really well, and you have to know if they're all zeros, how you can write them so they're not as big. And 1, 4, 2, 0, 0, 0. So they asked us, the question was, how many of each do we need to make to minimize our costs? Okay, so let's look at, this is our objective function, right? The cost. So which one is the smallest? Out of all these, this is the smallest cost, which means we need to make 1,200 of the audio players and 800 of phones to minimize our costs. All right, stop the video, do guided practice 3, and we'll see you in class.